Right now, while you are quietly listening to my voice, the massive ground beneath the state of California is stretching like a tightly wound rubber band ready to snap. Most people believe that an earthquake is just an unpredictable accident that strikes out of nowhere and ends in a couple of quick seconds. But brand new data from the highest resolution geological survey in American history reveals that an invisible, interconnected labyrinth of underground fractures has quietly shifted its stress balance across hundreds of miles. The solid ground beneath our feet is actively moving, and the newly updated hazard maps show that the danger zone has just expanded into areas that millions of families assumed were completely safe. If you're fascinated by real, grounded Earth science and want to uncover the powerful, hidden forces shaping our world without dramatic hype or exaggeration, take a quick second right now to subscribe to the channel. Join our growing community of curious thinkers who want to understand the true mechanics of our living planet before the major news headlines break. To truly understand why this new scientific update is sending ripples through the geological community, we have to look back at how human beings first began studying the shifting ground beneath North America. For thousands of years, across nearly every civilization, people assumed that the ground under their feet was completely solid, unmoving, and permanent. In the 19th century, as pioneers, ranchers, and early city builders established thriving communities, railroads, and harbors across the American West, they had no idea that they were settling directly on top of a massive tectonic collision zone where the outer shell of the Earth is slowly tearing itself apart. That peaceful assumption of permanent stability came to a violent and sudden end in the early morning hours of April 18, 1906, when an immense shockwave shattered the city of San Francisco. The violent shaking warped city streets into rolling waves, snapped underground cast iron water mains into pieces, flattened brick structures, and sparked catastrophic fires that burned across the city for 3 full days and nights. That historic catastrophe forced scientists to carefully examine a mysterious, jagged trench and scar running hundreds of miles through the California hills, which we now know today as the San Andreas Fault. A pioneering geologist named Andrew Lawson led a team of researchers along the path of the disaster and mapped the full length of the San Andreas Fault, discovering a truth that completely revolutionized modern geology. He proved that the land on the western side of the crack, which includes the coastal cities from San Diego to Los Angeles and up to San Francisco, is sitting on the Pacific Plate and creeping northwest toward Alaska, while the land on the eastern side is anchored to the North American Plate and sliding southeast. For many decades following this breakthrough, standard school textbooks taught students a very tidy, simple story about how this immense continental boundary operates. The early scientific model claimed that the San Andreas Fault was a single, clean, vertical slice cutting through the crust of California like a razor-sharp knife through wood. Early geologists expected that the Pacific Plate and the North American Plate would slide past each other at a steady, predictable speed like 2 freight trains passing along parallel tracks. They believed that mechanical friction would cause pressure to accumulate evenly along this single line, rupture at mathematically regular intervals, release its stored energy, and then restart the cycle like a giant underground pendulum clock. Under that original theory, estimating when and where the next major earthquake would strike seemed like a simple matter of basic arithmetic and historical record keeping. Geologists believed that all they had to do was calculate the average number of years between past major ruptures on a specific section of the fault, and they would be able to pinpoint the exact time window for the next big event. This neat, organized idea gave city planners, construction engineers, and early emergency managers a comfortable sense of security, assuming that earthquake danger was strictly confined to a single, easily drawn line on a map. What modern supercomputers, underground sensors, and satellite imaging have actually revealed over the past few years has completely dismantled that comfortable, simple picture. When scientists installed thousands of digital seismometers, underground listening posts, and satellite radar stations across the hills and valleys of California, they discovered that the plate boundary is not one clean line at all. Instead, the boundary is a chaotic, tangled, and highly complex web made up of hundreds of interconnected cracks, branch faults, and deep hidden fractures spreading outward for more than 100 miles on either side of the main trace. Some of these fault lines sit in plain view on the surface of the Earth, cutting obvious canyons, ridges, and valleys through the dry desert and coastal mountain ranges. But hundreds of other dangerous faults remain completely buried deep within the crust of the Earth, hidden miles below bustling suburban neighborhoods, crowded freeway interchanges, major international airports, and school playgrounds. The simple line once drawn in old school textbooks turned out to be an intricate, multi-dimensional maze of fractured rock where mechanical stress travels in unpredictable and dangerous directions. This fundamental difference between what early scientists expected and what is actually taking place beneath the surface matters tremendously for every single community in the region. When one underground fault snaps, its energy does not simply disappear into empty space once the violent shaking stops. Instead, that immense mechanical strain moves through the deep bedrock like a heavy weight shifting across a fragile wooden floor, directly loading up neighboring faults with sudden additional pressure. A quiet fault that has remained dormant for thousands of years can be pushed to its absolute breaking point in a matter of seconds by an earthquake happening miles away. Every single year, the relentless heat engine operating in the deep interior of our planet drives the Pacific Plate past the North American Plate at a speed of roughly 35 millimeters, or about 1.5 inches of motion annually. While 1.5 inches might sound like a tiny distance that you would never notice during your day-to-day life, it represents trillions of tons of solid granite and dense basalt grinding against each other with unimaginable geological force. If the rock was completely smooth and frictionless, the two massive plates would simply slide past each other smoothly, causing nothing more than a gentle, continuous vibration that would never cause any structural damage. The fundamental danger lies in the physical reality that solid rock is rough, jagged, brittle, and extremely sticky under the immense pressure of miles of overlying crust. As the deep mantle beneath the crust continues to drag the tectonic plates forward without stopping, the jagged edges of rock at the plate boundary catch on one another and lock tightly together. The massive forward energy that cannot be released does not vanish. Instead, it slowly bends, warps, and deforms the surrounding solid rock like a giant steel spring being cranked tighter and tighter with every passing decade. For years, decades, and sometimes centuries, that invisible elastic strain continues to accumulate in total silence miles underground, while millions of people commute to work, build houses, and carry on with their everyday lives right on top of the locked rock. The longer a stuck section of rock refuses to budge, the more terrifying the amount of trapped energy becomes within that specific zone. When the static friction holding the rough rock faces together finally gives way under the immense load, all that trapped energy explodes outward in a fraction of a second, sending violent seismic waves tearing through the crust. Have you ever stopped to consider that the solid ground beneath an entire state is quietly bending like a giant loaded spring right under millions of homes, bridges, and schools? If learning about how these massive hidden forces build up gives you a completely new perspective on the ground beneath your feet, take a quick moment to hit the like button and drop a comment below sharing your thoughts. To help modern cities prepare for these violent underground ruptures, the United States Geological Survey, widely known as the USGS, regularly creates comprehensive hazard maps called National Seismic Hazard Models. For many years, these hazard models were calculated using basic historical earthquake records and the known physical paths of visible surface faults. Experts originally expected that the highest shaking hazards would remain strictly confined to narrow corridors directly adjacent to the famous visible fault lines that had ruptured during recorded history. The newest hazard model update released by geological research teams has completely overturned those old assumptions in a dramatic way. By utilizing advanced airborne laser scanning known as LiDAR, which can penetrate through dense tree canopies, vegetation, and urban buildings to reveal the bare ground underneath, scientists discovered nearly 1,000 previously unknown fault lines crisscrossing the landscape. The updated hazard model revealed that the geographic zone, at risk of severe, damaging ground motion, has expanded significantly outward, placing millions more people into higher danger categories than ever before. This massive expansion of the danger zone matters because modern building codes, property insurance rates, and municipal emergency response plans are calculated directly from these scientific hazard models. When a map shifts to reveal that a quiet suburban valley can experience twice as much violent ground shaking as previously calculated, it means older hospitals, concrete highway bridges, water aqueducts, and residential buildings may not be strong enough to withstand the forces that could strike them. It forces civil engineers, city planners, and government leaders to completely rethink how we construct and reinforce our critical infrastructure to protect human life. One of the most concerning discoveries highlighted in the latest geological research is the widespread existence of what geologists call blind thrust faults. Unlike traditional strike-slip faults that slice through the surface of the earth and leave visible traces in the dirt, blind thrust faults are buried entirely deep within the crust and never break the top layer of soil. Because they remain hidden deep underground, they give no obvious surface clues about their exact locations or the massive amounts of elastic strain they are accumulating over centuries. Back in 1994, the immense danger of blind thrust faults was demonstrated in a terrifying way when a magnitude 6.7 earthquake struck the city of Northridge in the San Fernando Valley just before dawn. The disaster caused tens of billions of dollars in structural destruction, brought down major concrete freeway overpasses, collapsed apartment complexes, and took dozens of lives across the region. The event stunned the scientific community because the fault that caused the catastrophic shaking did not exist on any official hazard map at the time. It was a completely hidden blind thrust fracture buried miles beneath the valley floor. The latest mapping confirms that the entire Los Angeles basin and several surrounding inland valleys are underlain by a complex interconnected network of these blind thrust systems. To make matters even more challenging, these deep faults are tilted at an angle that directs seismic energy straight upward into the soft, sediment-filled basins where millions of people live and work. When seismic waves enter these deep, loose sedimentary basins, the ground behaves like a massive bowl of gelatin, trapping the waves and bouncing them back and forth between deep rock layers, which significantly amplifies the strength and duration of the shaking at the surface. For several generations, geologists also operated under the basic assumption that individual fault lines functioned as independent, isolated units that could only rupture one at a time. They believed that an earthquake starting on one specific fault would travel along that single crack until it reached the natural end of the fault segment, where it would run out of energy and safely stop. Based on this theory, scientists calculated the maximum possible magnitude of an earthquake in a given region simply by measuring the physical length of that single individual fault line. That comfortable, long-standing scientific assumption was completely shattered during the summer of 2019 near the desert community of Ridgecrest, California. A powerful magnitude 6.44 shock rattled the region on the 4th of July, followed less than 36 hours later by a massive magnitude 7.1 main shock. When scientists analyzed the satellite radar data and field measurements from the event, they discovered something that shocked the entire geophysical community. The rupture had not stayed on one neat fault line at all. Instead, the powerful rupture violently jumped across at least 5 distinct intersecting fault branches in a chaotic domino effect that scientists had previously considered nearly impossible. The earthquake demonstrated that when enough stress builds up in the crust, a rupture can leap across structural gaps in the rock and link multiple small, seemingly minor faults together into one massive, highly destructive catastrophe. This multifault rupture process means that even areas without a single giant fault line can experience unexpectedly large and powerful earthquakes through interconnected chain reactions. If you discovered that your own neighborhood was sitting directly on top of a hidden fault branch that was just identified by modern laser scanning, what changes would you make to your family emergency plans? Tell us your thoughts in the comments section below, and share this video with your friends and family so they can stay informed on how modern earthquake science is changing. Among all the dangerous geological features in North America, the specific detail that keeps seismologists awake at night more than anything else is the southern segment of the San Andreas Fault. This critical section of the fault runs from the Cajon Pass in the San Bernardino Mountains, down through the Coachella Valley, and ends near the shores of the Sultan Sea near the Mexican border. While the central and northern sections of the San Andreas Fault have ruptured and released their strain in historic events, like the 1989 Loma Prieta earthquake and the 1906 San Francisco disaster, the southern stretch has remained completely motionless. Scientists originally thought that this southern section might simply be moving very slowly, or that it was releasing its tectonic energy through harmless, continuous underground creeping rather than violent shaking. They hoped that the Earth was finding a way to relieve the pressure gradually without producing a massive, catastrophic rupture. For decades, researchers monitored the region looking for signs of regular, moderate energy release that would prevent a catastrophic buildup. What paleoseismologists actually discovered when they excavated deep trenches across the fault line was deeply unsettling. By analyzing ancient soil layers, broken rock strata, and carbon-dated plant fossils trapped in past earthquake ruptures, scientists uncovered the true history of the southern San Andreas Fault. They discovered that over the past 1,000 years, this exact segment of the fault has consistently produced a massive earthquake approximately every 100 to 150 years like clockwork. Yet right now, that very same southern segment has not experienced a major full-scale rupture since the year 1680, which is more than 340 years ago. This means the southern San Andreas Fault has gone more than 2 centuries past its historical average recurrence interval without releasing any significant portion of its stored energy. The tectonic plates have continued to push against each other relentlessly every single day during those 3 centuries, without stopping for even a single second. This enormous gap in time means the southern segment is currently suffering from a massive slip deficit of more than 25 feet of unreleased plate motion. The rock along this boundary is bent to its absolute physical breaking point, storing a staggering reservoir of mechanical energy that must eventually be released. World-renowned seismologists, including Dr. Lucy Jones, have repeatedly warned the public that the southern San Andreas is fully locked, loaded, and overdue for a major rupture that could easily reach magnitude 7.8 or higher. To truly understand what 25 feet of sudden underground displacement means in the real world, imagine standing on a quiet street corner where the ground on the opposite side suddenly jerks sideways by the length of 2 large delivery trucks in less than 10 seconds. That sudden, violent shift would instantly tear through transcontinental natural gas pipelines, sever long-distance fiber optic cables, knock down high-voltage electrical towers, and snap the massive concrete aqueducts that bring essential drinking water from northern mountains into southern California cities. Because major interstate transportation corridors and utility lines cross right over the path of the southern San Andreas Fault, a massive rupture there would instantly cut off major supply chains. The United States Geological Survey created a comprehensive computer simulation known as the ShakeOut scenario to model the full consequences of this exact event. The simulation showed that a magnitude 7.8 earthquake on the southern San Andreas would send seismic shock waves radiating outward at more than 2 miles per second through solid bedrock. As those powerful shock waves travel into populated metropolitan areas, the long-period ground waves would cause high-rise office towers to sway violently for up to 2 full minutes. Sandy soils with high water tables, especially near coastlines and riverbeds, would undergo a dangerous process called soil liquefaction, where the ground temporarily loses its solid structure and behaves like liquid quicksand, causing heavy structures and foundations to sink and tilt. To make this scenario even more concerning, the latest geological maps show that the southern San Andreas Fault does not operate in total isolation from other nearby fault networks. Running nearly parallel to it is the San Jacinto Fault Zone, which is historically the most active and frequently moving fault system in all of Southern California. Supercomputer modeling suggests that a major rupture initiating on the southern San Andreas could trigger an almost instantaneous secondary rupture along the San Jacinto Fault, unleashing a double punch of seismic destruction across neighboring communities. Meanwhile, in Northern California, another ticking geological clock is quietly running out of time beneath the heavily populated San Francisco Bay Area. The Hayward Fault runs along the base of the East Bay Hills, passing directly beneath heavily populated urban centers, major university campuses, hospital complexes, and municipal government headquarters. Seismologists often describe the Hayward Fault as one of the single most dangerous urban fault lines on the entire planet because of the sheer density of population and infrastructure located directly on top of its trace. Did you realize that millions of people in modern cities drive across locked, high-risk fault lines every single day on their way to work and school? Guess in the comments how many liters of emergency drinking water you have stored in your home right now, and take a second to subscribe so you never miss another deep dive into the real science of our dynamic world. When geologists examined the historical earthquake record of the Hayward Fault, they discovered that it has historically produced a major, damaging earthquake approximately every 140 years. The last major destructive event on the Hayward Fault occurred in the year 1868, when a powerful earthquake destroyed buildings throughout the East Bay long before the region grew into the modern, high-tech metropolitan hub it is today. Simple math shows that the region has now surpassed that historical 140-year average window. While the surface trace of the Hayward Fault shows minor signs of steady movement called aseismic creep, deep borehole sensors show that the main rock plates 5 to 8 miles beneath the surface remain tightly locked and stuck. The USGS developed a detailed disaster analysis known as the Hayward scenario to calculate the exact impact of a magnitude 7.0 earthquake centered directly on the Hayward Fault. The results revealed that such an event would trigger thousands of water pipe breaks, spark hundreds of major structural fires, and knock out internet and communications across the entire Bay Area for weeks. The modern reality is that our advanced cities are tightly interconnected systems where power, water, sanitation, and communication all depend on each other to function. When an earthquake breaks one critical link in that chain, the entire system can quickly grind to a halt. This makes understanding the exact mechanics of earthquake hazards not just an academic science experiment, but a vital matter of public safety and modern survival. The mystery of California's moving crust becomes even deeper when we look beyond state borders and examine how these fault networks interact with larger tectonic systems along the Pacific Rim. Just north of the San Andreas Fault, off the rugged coast of Northern California, Oregon, and Washington, lies the Cascadia Subduction Zone. Cascadia is a colossal 600-mile-long ocean trench, where the oceanic Juan de Fuca plate is being driven downward directly beneath the North American continent. Historically, scientists believed that the strike-slip faulting of the San Andreas and the massive subduction zone of Cascadia were two completely separate geological engines operating on totally independent schedules. They assumed that a massive earthquake in the Pacific Northwest would have no physical connection to what happened along the fault lines running through California. But deep-sea core drilling and marine sediment studies have completely rewritten that traditional view. Marine geologists analyzing deep-sea turbidite layers, which are underwater landslide deposits left behind by massive historical earthquakes, discovered a shocking pattern of synchronization. The data revealed that several major earthquakes on the northern section of the San Andreas Fault occurred almost immediately after massive, full-rip megathrust earthquakes in the Cascadia Subduction Zone. A magnitude 9.0 megathrust event in Cascadia releases so much seismic energy that it alters the stress fields through the Earth's upper mantle, acting as a direct physical trigger for faults hundreds of miles away. This critical revelation means that emergency management agencies cannot plan for earthquakes in isolated geographic boxes. A catastrophic earthquake along the Pacific Northwest coast could potentially set off a chain reaction of seismic activity that ripples all the way down through California, affecting millions of people, multiple major port cities, and nationwide supply chains simultaneously. Right now, as you listen to these words, an incredible network of high-tech scientific instruments across California is recording every microscopic quiver and shift in the Earth's crust. Thousands of high-precision GPS monitoring stations anchored deeply into solid bedrock are tracking the steady, unstoppable drift of the landscape in real time, millimeter by millimeter. Laser strain meters installed in deep boreholes drilled thousands of feet into the crust measure the tiniest stretching and squeezing of rock formations to track how stress is redistributing itself. In recent years, researchers at leading scientific institutions such as Caltech and UC Berkeley have pioneered an extraordinary new technology known as distributed acoustic sensing. By shooting high-speed pulses of laser light down existing commercial fiber optic cables buried beneath city streets, scientists can detect microscopic vibrations and movements in the ground smaller than the width of a single strand of human DNA. This breakthrough effectively converts thousands of miles of standard internet cables into a massive, real-time seismic nervous system covering entire metropolitan areas. All of this continuous, real-time data feeds directly into the ShakeAlert earthquake early warning system operated across the West Coast. There is a common public misconception that early warning systems are able to predict earthquakes days or weeks before they happen, like a weather forecaster predicts a coming thunderstorm. The scientific reality is that earthquakes cannot be predicted in advance because the tiny microscopic fractures that initiate a rupture occur miles underground under extreme pressure and heat where they cannot be observed before they break. What the ShakeAlert system actually does is take advantage of the fundamental laws of physics governing how seismic shock waves travel through solid rock. When an underground fault suddenly snaps, it produces two distinct types of shock waves. Primary waves, or P waves, which travel extremely fast but carry very little destructive energy, and secondary shear waves, or S waves, which move slower but deliver the violent ground-heaving motion that knocks down buildings and bridges. Ultra-sensitive seismic monitoring stations located right near the epicenter detect the fast-moving P waves the instant the rupture begins. Powerful computers instantly calculate the location and magnitude of the earthquake and beam an electronic warning signal at the speed of light to surrounding cities. Because radio waves and fiber optic signals travel at the speed of light, while seismic ground waves travel at the speed of sound through rock, the electronic warning arrives at your smartphone, computer, or automated control system seconds before the violent S waves reach your location. Those critical seconds of advance warning may sound brief, but they can save thousands of lives in a major disaster. A 10 to 20 second warning allows high-speed commuter trains to automatically engage their emergency brakes so they do not derail off bent tracks at 80 miles per hour. It allows utility companies to shut down automated valves on high-pressure natural gas lines, preventing massive post-earthquake fires from sweeping through residential neighborhoods. It gives surgeons time to lift delicate instruments from patients and gives school children and office workers time to drop, cover, and hold on beneath heavy desks before flying debris can cause injury. The ongoing updates to California's earthquake hazard maps are not a reason for panic or sensational fear. They represent the triumph of modern science in uncovering the true, complex nature of the planet we call home. Every new fault strand mapped, every blind thrust system identified, and every old assumption corrected gives structural engineers, emergency managers, and regular citizens the knowledge needed to build resilient communities that can survive the powerful forces of the Earth. The popular myth that California will one day crack open and fall into the Pacific Ocean is a complete Hollywood fiction that ignores basic plate tectonics. California is not falling anywhere. Its coastal cities are simply taking a slow, steady, million-year journey northward along the edge of the continent. The real challenge of living on this dynamic planet is learning how to understand, respect, and prepare for the natural movements of the world beneath our feet. To truly appreciate the full scope of this underground machine, we have to examine another hidden player in the tectonic equation known as the Garlock Fault. Running east to west across the Mojave Desert for over 160 miles, the Garlock Fault cuts perpendicularly straight across the north-south path of the San Andreas. For many decades, geologists viewed the Garlock Fault as a quiet, sleeping giant that rarely moved and posed little immediate threat to the major population centers located to the south. What field geologists and satellite interferometry teams discovered in the months following the 2019 Ridgecrest earthquake was completely unprecedented in modern observations. The violent ground rupture from the Ridgecrest event had transferred immense, measurable mechanical stress directly onto the northern edge of the Garlock Fault. Within weeks, satellite radar scans showed that a 30-mile stretch of the Garlock Fault had begun to creep and slip at the surface for the very first time in recorded modern history. This unexpected awakening of the Garlock Fault matters deeply because of its unique physical position as an underground hinge connecting the eastern California shear zone to the San Andreas Fault. If the Garlock Fault continues to slip and eventually produces a major rupture of its own, supercomputer models show that it could act as a direct physical bridge, transferring immense elastic strain straight onto the locked central and southern segments of the San Andreas. This discovery showed geologists that stress can travel around physical corners in the crust of the Earth, creating complex domino effects that span hundreds of miles of open desert. Another fascinating and critical area of study centers around what seismologists call the Sultan Sea stepover zone, located at the extreme southern tip of the San Andreas Fault. In this geothermal basin, the crust of the Earth is being pulled apart and thinned by underground volcanic magma chambers, pushing upward from deep within the mantle. Geologists originally expected that the extreme heat and fractured nature of the crust in the Sultan Sea area would cause tectonic stress to bleed off continuously in small, harmless microearthquakes without ever triggering a large-scale catastrophe. What scientists actually observed when they analyzed decades of swarm activity under the Sultan Sea was a far more complex and dangerous physical mechanism. The region regularly experiences dense clusters of hundreds of small earthquakes over the course of a few days, known as earthquake swarms. Detailed three-dimensional computer models revealed that these swarms are driven by high-pressure hydrothermal fluids migrating through deep fractures, and each swarm event redistributes stress directly onto the southern tip of the locked San Andreas Fault, acting like a tiny wedge tapping continuously at the base of a loaded dam. Every time an earthquake swarm occurs near the southern terminus of the fault, scientists at the USGS monitor the data around the clock with heightened alert levels. The mathematical probability of a major San Andreas rupture temporarily increases during these swarm episodes, because a small magnitude, 4 or 5 shake occurring at the exact physical anchor point of a locked fault line can act as the microscopic match that lights the massive geological fuse. It demonstrates how microscopic changes in underground water pressure can influence continental-scale tectonic plates. Have you ever imagined how strange it is that hot volcanic fluids bubbling miles beneath a desert lake could be the exact trigger that sets off a massive earthquake hundreds of miles away? If this detailed look into the underground plumbing of our planet is opening your eyes to how interconnected geology really is, let me know your thoughts in the comments and tap that thumbs up button right now. To make modern buildings and bridges resilient against these complex multi-fault ruptures, structural engineers have developed incredible new technologies that work directly with the physics of seismic waves. In the past, engineers believed the best way to protect a building was simply to make the concrete walls and steel beams as thick, heavy, and rigid as possible so they would not bend during shaking. What engineers learned from historical disasters in Mexico City, Kobe, and Christchurch is that rigid structures often snap and collapse when subjected to the violent, rolling frequencies of deep basin ground waves. Modern earthquake engineering now focuses on the concept of base isolation, where massive office towers and hospital complexes are physically separated from the moving bedrock by giant, flexible bearings made of alternating layers of steel and rubber. When the ground violently shifts back and forth beneath the building during a major earthquake, the rubber pads absorb and dissipate the kinetic energy, allowing the ground to slide sideways while the building above remains almost completely still. This brilliant engineering application transforms our understanding of wave mechanics into tangible physical protection for human lives. In addition to base isolation, modern skyscrapers are now equipped with massive counterweights called tuned mass dampers, suspended near the top of the building. When long-period seismic waves cause a tall building to sway to the left, the heavy computer-controlled pendulum swings to the right, generating an opposing physical force that dampens the building's motion and prevents structural fatigue. These engineering marvels demonstrate how human ingenuity can use the exact laws of physics to counteract the immense raw power unleashed by our shifting planet. When we zoom out and look at the vast expanse of geological time, we are reminded of how brief and fragile human civilization is compared to the ancient tectonic processes that shape our world. We construct our cities, pave our highways, and build our futures on a paper-thin, floating crust that rests atop a constantly churning dynamic interior. Understanding these deep geological rhythms is a powerful reminder that our planet is alive, dynamic, and constantly evolving beneath our feet, requiring us to approach the natural world with respect, scientific curiosity, and careful preparation. If you found this comprehensive breakdown of California's shifting earthquake hazard maps fascinating and want to stay ahead of the latest real-world scientific discoveries shaping our planet, please take a moment right now to subscribe to the channel and turn on the notification bell so you never miss an upload. What surprised you the most about this updated geological data? The hundreds of newly discovered blind thrust faults, the unexpected awakening of the Garlock Fault, or how long the southern San Andreas has been locked? Drop your answer in the comments below, and share this video with a friend or a family member who wants to understand the real science beneath our feet. Thank you so much for watching, and stay safe out there.